Hey kids, let's dive into series, right? We've been doing improper integrals, which, as I alluded to before, that's going to be the math that you did with that is going to be very similar to what we end up doing in series. But first, I want to do a little background from pre-cal because it has been at least a year, right, since you saw pre-cal and did series, and probably you would have done this series work remotely last year. So it might even be brand new for you. I hope not brand new, but it could be. So this series, you have probably heard of some famous ones. I hope, like the P series, the arithmetic series, the geometric series are all things that you should have seen from pre-cal. And they are all numeric series. And where we're going in calculus, as with most everything, we're going to try to turn something that was numeric into something that is algebraic. Okay, so that's where I'm going with these series. But first, I want to review pre-cal numeric series. You don't need this definition, but here is, no one's going to test you on this definition. But here's what you do need to know from this. We are going to be dealing with infinite series as opposed to a finite series. Series, by the way, means sum. So a finite series, for example, would be like 1 plus 2 plus 3 plus 4 plus 5. And that equals sum, right? 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5 is 15. So my sum, my finite sum would be 15. An infinite series would say, for example, 1 plus 2 plus 3 plus 4 plus 5 plus continue that pattern is an infinite sum. And just like with convergent and divergent improper integrals, I want to know if an infinite series, if that sum, right, if the sum of all of those terms, will they continue to grow without bound, bust out the house, or will they stay within a house? Certainly, I hope you can see that if I'm adding 1 plus 2 plus 3 plus 4 plus 5 plus 6, right, that sum is going to grow without bound. This is a divergent infinite series. So here is abstractly what a series looks like. Each one of these individual terms form a sequence. A sequence is a list of terms. We are hardly ever going to deal with a sequence. A sequence is a list of terms, not a sum of terms. A series is a sum of those terms going to n. And of course, I can expand my infinite series like this, or I can collapse it with summation notation and say that I start with my first term and go my a sub 1 and go all the way to infinity. Now in pre-cal, there's lots of different ways. Hopefully you learned a lot of different ways you can manipulate the summation notation. I can change this to a 0 if I wanted to make this the a sub 0 term, right? There's lots of things that I can do. The numbers, because we are dealing with a numeric series, the numbers with commas form a sequence, and they are the terms of the series. The series, again, means you're adding the terms. We call a sub n the nth term. So, for example, now in our curriculum here in our school, in our county, we put numeric series in pre-cal, whether it was magnet pre-cal, whether it was honors pre-cal, it doesn't matter. This objective is in pre-cal. However, AP Calculus has numeric series as an objective of their curriculum, which means you could straight up see a numeric series question on the AP exam. It will be on a multiple choice question though. So could you take this expanded series where this is the first term, this is the second, third, and fourth, and going on to a sub n. Writing in summation notation means, can you collapse it? And give me one expression that represents all of these. So here are the things that I think to myself. Self, I've got a fraction. So I certainly have to have whatever I'm going to write is going to be a fraction. Do you see a pattern in the numerator? I hope you do. I hope you can see it's powers of 5, right? This is 5 to the first. This is 5 squared. This is 5 cubed, and that's 5 to the fourth. So I kind of have an idea of how I could write the numerator. Now look what's happening in the denominator. The first thing I notice are yell points, right? Those exclamation points. 3 factorial is 3. It's not 3, right? So it's 3 times 2 times 1, which is 6, right? This is actually 2 factorial as well, isn't it? Because it's 2 times 1. So do you see a pattern with factorials in the denominator? So again, I see powers of 5 in the numerator. I see factorials in the denominator. What else do you see in the denominator? And I hope you see powers of, right? What do you have here? You have a 1. Well, that's anything to the 0. What's 8? 8 is 2 cubed, isn't it? What's 27? That's not 2 anything. Oh, wait, it's 3 cubed, isn't it? Hey, what's 64? Oh. So do you see how I use my factoring brain? And I picked apart I said I have a fraction. Do I have a pattern in the numerator? Do I have a pattern in the denominator? Now I have to relate that pattern to the term. Is that a good way to say it? So in other words, this to the term. So here's my first shot. Let me think. So my first shot was I put my powers of 5 to the n, right? Because the power 1 matched a sub 1, 2, 3, that all matched. Then I had the same thing here, right? The 2 got cubed. A sub 3 had a 3 cubed. A sub 4 had a 4 cubed. So I wrote n cubed in the denominator. Then I noticed because after all, what is this? This is 1 cubed, right? So how did I get this part? Do you see what I did? How was 2, 3, 4, and 5 related to sub 1, sub 2, sub 3, sub 4? It was my n plus 1 more, right, for each one. So just kind of guess and checked. Now I'm going to say, did I start at the right place? And since I'm going off forever and ever, I'm going to put infinity. And I'm going to check, is this right? Nah, I don't think so. I haven't done anything wrong, but what haven't I taken care of? The alternating signs, right? And there's a variety of ways I can write alternating signs into, there's one way, right there. This is not the only way, but that is one way to get my signs to alternate. What does it mean? I don't want to change the value of any of the fractions, so I want to multiply it times 1, but I'm going to multiply it times -1. And since I'm starting with n is equal to 1, what is 1 minus 1? 0. What is -1 to the 0? 1. That means this first fraction will be 1 times a positive number, and that's what this is, positive to begin with. But then when n is 2, 2 minus 1 is 1, negative 1 to the first is negative, so the second term will be negative, and so yada, yada, yada. But, right, I didn't just look at that and write the summation notation. I built it. And then I checked it. And that's, right, and the more you do, and you have to do a bunch of them, the more you do, the better you get. And the faster it gets. All right, now I'm going to come back to that, but I want to get to this idea here that, sorry, I want to talk something about partial sums of an infinite series. Partial sums just means you stop and start. Stop and sum, and then start again. This concept is not a big deal to you. If this stuff throws you, I don't want you to worry about it, but I just want you to realize what this is saying is if you add the first term, you get the first term because you're adding nothing to it. The sum of the first two terms is whatever a sub 1 sub a sub 2 is. This list here are called partial sums because you stop after the first, you stop after the second, you stop after the third, you stop after the nth. And as soon as I stop, I'm really not infinite anymore. I'm finite and I'm going to sum. So you do not need to write any of this stuff down, but here's, right, you're going to be writing stuff down in the next slide. But the important piece of this, if the sequence, I want you to think terms. If the terms of what we call the partial sums, don't worry about what it's called. I just want you to think terms. If the sequence of terms has a limit, that is a number, as I go off to infinity, we say the series converges. That means the sum is getting so infinitely small as you go off to infinity that you're going to reach a maximum. It converges to this sum S. It's an infinite sum, but it's bounded. And we don't write that at all. Don't worry about writing that at all. The important thing here is otherwise, not the sequence, the series diverges. Again, as I said in improper integrals, we don't really care about divergent series or divergent improper integrals, right? We want to know if they're divergent so we can throw them away. We want to keep and collect all convergent series. Those are the ones that we're after. That's what we like. So, how can I tell if my numeric series converges or diverges? This is a huge question. This is a huge question that has no simple answer. The answer depends upon what series you have. However, I can look at any series and I can tell right away if I can chuck it. What kind of series do you want to chuck? Anything that diverges. So all that whole previous slide, right, where I said don't really, right, just kind of look at it and try to absorb what I'm saying. The important piece here, if you have an infinite series that converges, let me tell you that, wait a second, that's the hypotenuse. Hypothesis. That's the if part. Here is the then part. If the infinite series converges, then the limit of the terms is 0. This is not helpful. This is not helpful because no one gives, well, I shouldn't say no one, but generally you're not starting with the knowledge that you have a convergent series. You want to be able to tell. How can I tell if my series converges or diverges? This theorem says if you converge, then the limit of the terms is 0. Not helpful because I want to know if I have convergence. And the danger in this theorem is that kids use it backwards. They say, oh, that means that if the limit of the terms does go to 0, I automatically have convergence. No, come on, right? If it is raining, then I have an umbrella. Does not imply that if I have an umbrella, it is raining, right? That is P arrow Q. P arrow Q is an if-then statement. The conclusion, the then part, can only be true if the hypotenuse is true. Did I say hypotenuse again? Hypothesis is true. However, if you say the conclusion is not true, it does imply that the hypothesis is not true. I said hypothesis instead of hypotenuse that time. So if you negate, here, right, the conclusion says the limit of the terms is 0. If you say if you know that the limit of the terms is not 0, something I can figure out, then the opposite of the hypothesis has to occur. That's called, it's supposed to be then, no, I should have a then there. Then the series must diverge. That's called the contrapositive. For those of you that remember anything about your logic lessons, if P arrow Q is your if-then statement, this hypothesis, remember, was that I have a series that converges, but no one gives me that. Hello. The converse is not true. The converse would be if limit of terms is equal to 0, then converge. That is logically not equivalent. That is not true. However, the contrapositive is logically equivalent. Yay. If you negate the conclusion, limit of terms not equal to 0, then you definitely know the opposite of the hypothesis or the conditions. Not converge, which of course means diverge. I make such a big deal about this because this is your first test. It is the only test for divergence. So somewhere in your notes, please make a list of tests. We're going to be adding to this over the next couple of lessons. The list of tests. You only have one test for divergence. The test for divergence is if the limit of the terms, not the series, every other test that I'm going to give you is going to be a test for convergence. There is one and only one test for divergence, but it is a simple test to run, and you should always run it first. Always. You don't know what it means yet, really, to run any tests on something, but trust me, you're going to get lost of experience. The name of this is called the nth term test for divergence. That's the name of it. There it is spelled out. If the limit of the terms, K means terms, does not equal 0, then your series with all the sums in it will diverge. So for example, look at this numeric series. 1, -1, 1, -1, 1, -1. This is kind of tricky because you're like, well, that sum goes to 0, right? You're just adding 1 and -1, -1. But The idea of converging means that your sum is approaching a level, approaching a maximum value, not that it just bounces back and forth. So how do I answer this? I look at the limit of the sequence. Notice I took out the pluses and I replaced them with commas. Does 1, -1, 1, -1, 1, -1? Does this list go to 0? Not the sum. I know the sum. I know what you want to do. You want to try to add them. I mean this list. Does it go to 0? No. The sequence has no limit. It bounces. Boing, 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 boing. 1, -1, 1, -1, 1, -1, 1, -1. It just bounces as you go to infinity. The sequence has no limit. The limit of the terms does not equal 0. Therefore, this series with the pluses diverges. And I know that's hard to think of. Let me give you an example of converge. Well, no. Let me give you an example of a series where you can kind of see where the terms are going. All right. Hopefully you can see that those terms are getting smaller and smaller. Take out the plus sign, replace with commas. Are these terms, is this list going towards 0? Yes. The sequence does have a limit as the terms go to infinity. The limit of the terms is 0, therefore, nuttin', honey. Nuttin'. Your test, you only have one test to be able to run, and it is a test for divergence. Since this sequence has a limit that is a number that is not equal to the limit of the terms is equal to 0, I cannot make a conclusion. My sequence might converge or it might diverge. I have to do more tests on it. So I told you only have one test for divergence. All your other tests that I'm going to give you are going to test for convergence. And if your series fails your convergence test, then you diverge. That is not true for the nth term test for divergence. If your series fails the nth term test for divergence, inconclusive. You have to do more tests. Dagger. All right, let me start to narrow our scope. I want to look at some numeric series that are pretty famous. And the first famous one we're going to look at is the geometric series. So here's an example of a geometric series. That's just the one that we had, right? What makes it geometric? Do you remember from pre-cal? Probably not. That's okay. It is the fact that how you move from one term to the next is multiplying by a common ratio. Means fraction. And we call that common ratio R. So how do I get from 1 to 1/2? I multiply by a half. How do I get from 1/2 to 1/4? I multiply by 1/4. How do I get from 1/4 to 1/8? I multiply by a half. Therefore, my common ratio is a half. And I can rewrite each one of my terms this way. The first term is 1 times 1/2 to the 0. The second term is 1 times 1/2 to the first. We call this A times r to the n. A is 1 and r is 1/2. So you do need to be able to recognize a geometric series. Remember, an arithmetic series, we're not going to deal with arithmetic series too much, right? An arithmetic series is when you move from one term to another by adding a term. By adding the common difference. Those series are going to diverge, right? Because you keep adding a positive number or adding a negative number, and this, right? And those terms go off, and their sums go off to infinity, negative infinity, as the case may be. From pre-cal, you do need to know that a geometric series, a geometric series will converge if your common ratio is less than 1. Actually, the absolute value of your common ratio needs to be less than 1. So I can have a ratio that is negative. That'll just alternate my signs for every odd power of my ratio. I'll have a negative. So once I identify my R and my A, geometric series have a formula for the infinite sum. If you converge, the geometric series will always converge to the infinite sum A, which is the first term, divided by 1 minus your common ratio, not the absolute value of your common ratio, your actual common ratio. And for us, since our R was 1/2, and our first term was just 1 times 1/2 to the 0, which was 1, two is the top of my house. So this infinite sum, if you keep adding, right? So remember the previous example where I ran the nth term test for divergence? This series failed, if you will, the nth term test for divergence. So I wasn't sure whether it was going to diverge. It was still possible to either converge or diverge. Then I recognized it as a geometric series, and I ran the geometric series test for convergence. So the geoseries test for convergence if the absolute value of your common ratio is strictly less than 1, then not only does your geoseries converge, it converges to the infinite sum, first term divided by 1 minus your common ratio. If you fail this test, in other words, your common ratio is 1 or greater than 1, if you fail the geo test for convergence, your series diverges. So, does this series converge? If possible, find the sum. If they ask you for the sum, hint, it's probably geometric. There's going to be lots of series that we can eventually find out if they converge or not, but only geometric can we find the sum. Do we have a formula to find the actual sum? Otherwise, we're just going to be able to say it converges. So what do I have here? To find this find if this series converges. I need to, now this is nice. I love it. I love the fact that it's already in summation form. So I can see my R. So A is your first term. R is your common ratio. The absolute value of R is the absolute value of 3/5. That is less than 1. Therefore, this geoseries will converge by the geoseries test. Further, it will converge to the infinite sum, 1 minus 3/5. And remember, A is my first term. My first term comes when I put a 0 in for n. So I have 2 over 5/5 minus 3/5, which is 2 over 2/5, which is 2 times 5/2. Which is 5. Okay. What if, be careful, right? Pay attention. What if n had been 1? How would this change? Think about that for a minute. Well, nothing over here would change. My 3/5 would still be my common ratio. The absolute value of 3/5 is still less than 1. Therefore, I still am going to converge by the geometric series test. But what is my first term now? What's going to change is my infinite sum. My first term is 2 times 3/5 to the first. If you think about it, that is just 5 minus the first term. Right, when your first term was just 2 to the 0, right? Because you're just, if you started at 1, you've kind of your list of terms, you just like erase the first one. So it's 5 minus 2. Kind of cool, right? What was important is that you recognized you had a geometric numeric series. And then this math became pretty simple. This geometric series converged by the geometric series test, and I was able to find the infinite sum. Okay. Oh, did that already. What about this one? Okay, it's not quite in my geometric series, right? Does the series converge? Is it a geoseries? As soon as I see these, right? As soon as I see something to an n, oh, I have a negative. Boo, boo. Hey, by the way, this for square, I don't know exactly what the square root of 3 is, but it's like 1.7-ish, right? What do you do with a negative exponent? How can you take that negative exponent and make it positive? I took algebra 1 and I paid attention. Look at that. So what is your A this time? Your first term? And your R. Always go after your R first. My common ratio looked like it was smaller than 1, but not with this negative exponent, it wasn't. Since by the geoseries test, I failed, this series must diverge. So let me go back to this geometric series, right? Where we had, this was, right, one of our first examples. And we had our common ratio was a half, right? I didn't write it like this at first. I wrote it as 1/2. I'm sorry, 1 plus 1/2 plus 1/4 plus 1/8, right? This is a numeric geometric series because we could write it in this form, where we moved from term to term by multiplying by this common ratio. Well, kids, what if I replace that number r with a variable? In other words, what if I cover it up? What if I say, I'm not going to tell you what the common ratio is. I'm going to hide it. I don't have a numeric series anymore. I'm going to drop variables in there. I'm going to keep the exact same form of the geometric series, but I'm going to drop an x in for a half. Everywhere I see in 1/2, I'm going to put an x. Oh, snap. Now, you know that x is a half. You know by the geometric series the common ratio is less than 1, and therefore this numeric series converges. But pretend you don't know that the common ratio is a half. You know there's a possibility that this geometric series will converge, only if x represents a number that is less, whose absolute value is less than 1. What? What? This is called a power series. Hello, I took a numeric series and I morphed it into a power series simply by covering up the common ratio and not telling you what it is. You can't see it. You can't see it. It's an x. Your numeric series has become a power series. I got the power. Boom, 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 boom. Gee, I wish, what is that? The CC Factory? CC? I don't know. Great song, regardless. This is a power series. Hold the freaking phone, though. Kids, kids, kids. This power geometric series, look what happens if I clean this up just a little bit. 1x to the 0 is 1 plus, oh crap. It's going for some big news here. Big, big news. And I forgot to turn my pen on. This is 1 plus x to the first plus x squared plus x cubed plus, I hope you're sitting down. For God's sakes, an infinite geometric power series sure looks an awful lot like an infinite polynomial. And you know what? You know an awful lot of crap about polynomials. You know a lot about polynomials. Oh my gosh. Life just doesn't get better than this. I'm going to ask you if this power series, see the x? It's not a number. Does this power series converge? If possible, find the sum. What? You just need to think of this x as your common ratio. And what does x have to be in order to get a convergent series? And remember, the power now in the algebra, remember I told you what we want to do is collect as many convergent series as we can. I now have a representation, x to the n, for a whole bunch of convergent series, given that you make sure that common ratio, which I call x, is less than 1. Bam! Bam! Sure as heck is geometric. Can you find the sum? I think so. That, my friends, is to be continued. Whoa, big news, big news. All right, I will see you in our next live session.